All right, hello again. Let's get into the next topic, which is probability. Now, this is a topic that is not really investigated in your textbook, but it's one that's extremely important for you to know. I'm sure you all have been exposed to these topics before, but this is you can consider this to be a refresher on those topics. Just basic probability theory. I want to introduce, get you a refresher on these concepts before you proceed in the textbook to other topics. Probability is really foundational to understand for statistics or many other areas of mathematics. In this topic in eCollege, you'll see that I also have a link to learn more about probability at a website called Hyperstat, which has some great probability information. And another site that I have linked in the topic is to learn about Bayes' theorem, which you might have heard of before. It will require you to have a pretty firm understanding of the basic concepts of probability I'll be talking about today, but it's extremely important. Bayes' theorem, as you'll see, it's what you need when you're thinking about real-world examples of probability. Most real-world examples, such as what is the probability that you have a particular disease? What's the probability that you're pregnant, given a positive test result? Okay, any kind of questions like that in the medical domain, it's valid. But it's not just the medical domain; it can be almost anything, really. Within my own area, a research area of eyewitness identification, you can ask, what is the likelihood that a suspect is guilty given that he was chosen from a lineup, okay? And as you'll see with Bayes' theorem, it requires information about what are called base rates in the population. So how likely is it that police have that police tend to get a guilty suspect in a lineup? Okay, you may not always know what the base rate is, but anyway, you'll learn more about Bayes' theorem, and that's good stuff, very important. But first off, let's get into some basic probability concepts here. Okay, so a probability is defined as relative frequency of occurrence. It has these basic definitions here. A sample space, which are all possible outcomes of, you can call it an experiment. Okay, we'll stick with that definition. An elementary event is a single member of the sample space. An overall event is any collection of elementary events. And probability can be shown as the following here. P, of course, we've seen stands for probability. So probability of an elementary event equals 1 divided by the total number in the overall space. Probability of an event is the number in the event over or divided by the total number in the space. And we'll see some examples of this in a moment here. You'll see the term conditional probability quite often. This is the probability of A given B. So we've seen that vertical line before. That just means given B. And as we'll see with some examples here, you always want to focus on the B part first to narrow down to the area in the space that you're talking about here, and then you count up the instances of A. Okay. So whenever you see that given line, always focus on the second symbol first. The second number, it'll designate either a row or a column in the space, as we'll see, and then you count up the instances of A. So probability of A given B is the number in A and B divided by the number in B. Okay. So some basic formulas for you to memorize here for probability. The probability of A for conditional probability here is the redefined sample space of B. So you're narrowing down to just the B part of the sample space, and then you're talking about what part of B is qualifies as A. Okay. So let's get into this example here. This was a mock jury study in which you have two different kinds of juries. An authoritarian jury, which they're instructed to respect authority, or they're already people who have some kind of overt respect for authority, versus a more egalitarian jury. Don't worry about the specifics here of this study, just I want to give you these definitions. Egalitarian, equal rights for all. Okay, and in this study, let's say the researchers were curious about the type of jury here, kind of their political stance, if you will, and how that leads to them deciding whether the defendant gets gets an award or not. So let's say that it is I'm sorry, not the defendant, the plaintiff rather, whether the plaintiff gets an award. Okay, so let's say it's someone whose husband died of lung cancer, and they're suing a tobacco company or something. Okay, so how likely is the mock jury, to give the plaintiff, the wife of the deceased, an award, a big $1 million award or something, versus no award? Okay, so that's basically what we're dealing with here, but really we're going to be focusing on these numbers to iron out these probability issues. So the overall sample space is all 48 jurors. This is the N. This is the overall number of participants that you have. Okay, participant jurors in this case. An elementary event is any one of those 48 jurors. Okay, and so they're being counted up in these 4 cells here based on the condition. Okay, but each one of those is an elementary event. An event, a whole event, is any subgroup of the 48. Okay, for example, the 31 here that decided to give an award. Okay, any one of these quadrants is a conditional probability, as we'll see, and any one of these totals, kind of marginal totals or marginal probabilities, as they're called, if you divide by 48. These are all events. Okay. So let's get into probabilities here. Okay, probability of an elementary event, just 1 out of the 48 is, well, 1 divided by 48. Probability of an award, so probability of a particular event, namely award in this case, is 31 out of 48. A conditional probability is one of these 4 cells, probability of award, given authority. Okay, so as I said, you first want to focus on the second part here. First, you want to look for the authority row or column. In this case, it's column. So look for the authoritarian column, and then you look for the award part. So you know you're only going to be dealing with this half of the sample space, and you're looking for the award part. So the award part is here. 18 divided by 20 is the conditional probability there. As I said, the 20 authoritarian folks are the reduced sample space that you know you're dealing with because it's given this half of the space. Always do the denominator first, in other words. Denominator is 20. The second part of this equation is authoritarian. Okay. Out of the 20 authoritarian jurors, the 18 who gave an award go in the numerator. So in terms of when it comes to probability, they're the big 3, as they're called. First one being independence, which means that events A and B are independent if the following is true. If the probability of A given B equals just the probability of A, then you know that they're independent. Okay, the A probability is not changed by reducing the sample space to B. I'm not saying that this is the case with the artificial data I just gave you about the jurors, but this is just a definition. The multiplication, or it's also called the AND rule, goes as follows. The probability of A and B equals the probability of A times the probability of B given A, which is the same thing as saying it's the probability of A given B times the probability of B. Okay. Another one here, although I'm not counting it as part of the big 3, although I suppose you'd call it the big 4, is the mutual exclusivity rule, if you will, which is that events, and it's different from these other ones. Okay, some people think that independence and mutual exclusivity are the same thing. They're not. Mutually exclusive events are as follows. Events A and B do not have any elementary events in common if they're mutually exclusive. Events A and B cannot occur simultaneously. So we'll see some Venn diagrams to portray these rules. But for now, just understand that probability of A and B equals 0 according to the mutual exclusivity rule. And the third of the big 3 is the addition, also called the OR rule, in which, and this is the more complex of the 3 because it does involve the multiplication rule as well. Probability of A and B equals probability of A plus probability of B minus, and here's the multiplicative rule or multiplication rule, minus the probability of A and B together. So let's step through each of these in turn while using this mock jury example. So the same data we saw before. The first of the big three, let's look at independence here. Is award independent of authoritarian? Okay, so we're looking at a row versus a column here. These two are in fact independent if the probability of award, okay, equals probability of award given authoritarian. So let's break this down here. The probability of award, so now we're just talking about one row, and that's it, is 31 divided by 48. Okay, so we're not talking about any of these individual cells. We're only talking about the probability of award. This whole row, 31 divided by 48, is 0.65. And probability of award given authoritarian, so based on the rule I already told you, you want to first focus on this part, just the authoritarian part of the sample space, so just that column. Now you look for award 18, and you're dealing with just this column. So 18 divided by 20 is 0.9. Yes, these are not the same. Okay, award is not independent of authoritarian because 0.65 is not equal to 0.9. Another example here is no award is this row independent of egalitarian, this column. It is if the probability of no award equals the probability of no award given egalitarian. Well, let's look this through here. The probability of no award is this row, 17 divided by 48, the overall sample space. Probability of no award given egalitarian, so it's given egalitarian, so we're dealing with this column. No award, dealing with 15 out of 28. Indeed, 0.35 is not the same as 0.54, so these also are not independent. A bit more about independence here. A is independent of B if the probability of A equals the probability of A given B, or if the probability of B equals the probability of B given A. So, important to keep those in mind. Some more examples here. If the probability of A is 0.3 and the probability of A given B is 0.4, are they independent? And so you're given these numbers here, and you're asked, is A independent of B? And explain. I'm just going to give you these and ask that you pause the lecture here so that you have time to kind of write these down and try to answer each of these questions. The answers will be provided at the end of this lecture here, but go ahead and pause the lecture now and see if you can come up with these answers. Very important to do this. Okay, going to go ahead and continue on now. All right, another example here, arguably a more fun example. People in a restaurant were asked before and after their meal if they thought they would like a dessert. So the question that you can ask is dessert independent of before? So dessert, this row, is it independent of this column before? So the probability of dessert, this column as a whole, this row, is 55 divided by 104, 0.53. Is it the same as the probability of dessert given before? So it's given before. We know we're dealing with this column. Look for dessert. 34 divided by 52 is 0.65. Indeed, they are not independent. These are not the same. Let's see. You can also do it the other way around. Probability of before is 52 and 104, or 0.5. Probability before given dessert, so now you're restricting it to just this row, the dessert row. Now you look for before, 34 out of 55, 0.62, also showing, just like before, that they're not independent. It's going to show it either way you look at it, that they're not independent here. So which two probabilities would you have to examine to determine if no dessert is independent of after? Well, hopefully you understand this by now. Two ways of doing this, just like there was up here. You can either look for the probability of no dessert, this row here, see if it equals the probability of no dessert given after. So given after, probability of no dessert, so 31 divided by 52. Or you can look for the probability of after, see if that, the 52 divided by 104, equals the probability of after given no dessert. So narrow down to no dessert, look for after, see if 31 divided by 52 is the same thing as 52 divided by 104. I think we're going to find that they are not independent here. Okay, so let's move on to the multiplication rule here. back to our mock jury experiment. The second of the big three, multiplication rule. Probability of A and B equals probability of A times probability of B given A, which is the same thing as probability of A given B times probability of B. And this is, as you can see, the product of two probabilities, one about A, one about B, what are called marginal versus conditional probabilities. So the probability of A or the probability of B by itself, these are called marginal probabilities. Basically, you're looking at, let's say A is a ward, well, you're looking at the margins. Okay, let's say B is authoritarian, you're looking at the margins. That's one way of describing why it's called marginal probability. And another is a conditional probability. So probability of A given B, for example here, that's conditional because it's conditional upon B. Whenever you see that vertical line for given, probability of A given B, it's a conditional probability. You're dealing with one of these four cells. You can't talk about one without talking about, you can't talk about one sort of variable here without talking about the other. If you're talking about these four cells, they're completely conditional. So let's go ahead and compute something here. Probability of award and authoritarian. Well, we know the answer here is 18 divided by 48, or 0.375. Okay, award and authoritarian. But let's break this down. It is the same thing as the probability of award as a whole, which is this row, 31 divided by 48, okay, times probability of authority given award. So you're given award, you narrow down to this row for award, then you look for authoritarian, 18 divided by 31, and you multiply those two together, and sure enough, you get 18 out of 48, 0.375 again. You can also do it the other way around, probability of award given authority times probability of authoritarian. Sorry, I'm calling it authority versus authoritarian. Either way, you're also going to end up with the same number here. Well, what about another example of multiplication rule? Probability of award and egalitarian. Well, it's clearly 13 out of 48 here. Let's see if we can match that by working with the multiplication rule. Well, it should be the same as, well, both of these. Probability of award, I'll just do one of them. Probability of award is 31 out of 48 times probability of egalitarian given award. So you're given award, egalitarian is 13 out of just award, 31. There you go. And sure enough, 13 out of 48 is the answer. Okay, same thing if you do it the other way around based on the other example here. Okay, so finally some Venn diagrams here so we can see how this looks. Here's the formula again for the multiplication rule. When we take the product of two probabilities, we get an answer that is actually smaller than either of the two probabilities by themselves. We're taking a fraction of a fraction. Okay, the probability of A and B is called a joint probability. It's literally where these two different probabilities, A and B, where they join together, where they overlap. So the probability of two things happening together has to be less than the probability of either one by itself. So the probability of A and B, it's this overlapping segment right here. Okay, clearly it has to be smaller than A by itself, and also has to be smaller than B by itself. Okay, now what about mutual exclusivity? As you'll see here, this is different from independence. Basically, it means that the probability of A and B equals 0. So if they're mutually exclusive, that means there is no overlap of any kind, and it doesn't make any sense to use a multiplication rule. Not one of the big three, not the same as independence here, but still important to understand. Are no award and this row here and authoritarian, are they mutually exclusive? Well, if none of the 48 jurors had responded in this cell, award and authoritarian, there's, no award and authoritarian, so there's two here. If it had been 0, you can say that they're mutually exclusive, but they're not. There's a couple people in here, so they in fact are not mutually exclusive. However, if are award and no award mutually exclusive? Well, yes, they are. I mean, based on the design of this experiment, you can only be in one or the other category here. So if A is award, B is no award, yeah, you got to be in one or the other. Indeed, they are mutually exclusive. Okay, on to the addition rule. All right, this is, again, the probability of A or B equals probability of A plus probability of B minus probability of A and B. So, as I said before, this is the most complex of the three because it uses the multiplication rule to get its answer. Multiplication rule is right here. First, compute the probability of award or authority. Now, let's see how this works here. Whoop, keyboard lost for a moment. There it is. Okay. So what is this? It's the probability of award, which is just this top row, 31 divided by 48, plus the probability of authoritarian by itself, which is this column, 20 out of 48, minus the probability of both together, award and authoritarian, which is here and here, 18 out of 48. So you run the numbers, you get 0.69. Now you can compute the probability of award or egalitarian. Now you run the numbers here, probability of award, again, this top row, 31 out of 48, plus probability of egalitarian, this column here, overall, 28 divided by 48, minus probability of award and egalitarian, award, egalitarian together, 13 divided by 48, and you get 0.96. Okay. So what we're looking at here with the addition rule in terms of a Venn diagram is that this probability is the area in A plus the area in B, but eliminating the overlap. Okay, so I'm not really showing it that well here, but you want to take this overlapping portion and remove it. Okay, that's basically what the addition rule is it removes the overlap and just doesn't include it at all. Okay, so it takes A plus B, it just doesn't include any overlapping section. All right, more about independence here. Now here are the answers to hopefully what you did before was pause the lecture and come up with these answers yourself. If you haven't done that yet, well, go back and please do it now. But okay, here come the answers. A is independent of B if, well, that's just the formula again. I'm not going to keep reading it to you. And here are the answers. Okay, so for that first one, A and B are indeed not independent because, hey, they have these two have two different results here. 0.3 is not the same as 0.4. Sorry, that point should go with the 3 here. Second one, no, A and B are not independent here either because 0.1 is not equals to 0.3, or the other way of doing it will give you 0.2 and 0.4. And this one here, yes, A and B are independent. Finally, you get an example in which they actually are independent, and because you're finding that they're the results are the same, 0.1 to 0.1 or 0.2 and 0.2. And finally, this one gave you three options here. Which of these is the reason that A is not independent of B? And here's the answer there. 0.34 is not equal to 0.49, and that's the reason. So don't move on to anything else now until you understand how all of these answers were arrived at. Okay. Continue on with the online information I provide for you in the eCollege topic for this week on probability. Once you feel that you have a solid understanding of the big three here, as well as mutual exclusivity rule, go ahead and move on to Bayes' theorem. Okay, and I have that link in this topic as well. Feel free to go to the discussion board in this week or email me if you have questions. I'll be happy to address those.